Okay, in this podcast we're going to talk about covalent bonding. So in the covalent bonding model, if you think about fluorine, it's got 2 electrons in its innermost shell, and it's got 7 valence electrons in its outermost shell. And when 2 fluorines come in contact with each other, they still both have their 7 electrons, but in order to lower in energy, like we talked about, they want to have 8 electrons in the outer shell. So what happens is 2 of those electrons end up becoming a shared pair between the 2 atoms. Okay? And they still have the other 6 that are not shared. And that becomes the bond. That's the covalent bond. Okay, so what is a covalent bond? Well, it's the sharing of electrons. And why does it bond? Well, if you think about what's happening, if I have a 1 hydrogen atom, it's got a nucleus and an electron around it. I have another hydrogen atom, it's got a nucleus and an electron around it. And what happens is, down here, you can see this electron, because it's negative, is going to be attracted to this positive nucleus. This electron is going to be attracted to this positive nucleus, and they're going to come together, be attracted to each other, and come and form this bond. And in the process, they both end up with a full outer shell. Okay, so it's this mutual attraction that causes them to come together. That's the attraction. If they get too close together, though, and the nuclei are too close, those nuclei are going to repel each other. So there is this sweet spot where it's just the right distance between them, where there's attraction but not too much repulsion, that causes them to be low in energy, which is the favorite condition, and makes them bond. And when they bond, they end up with this cloud of electron density in between the 2 atoms. Okay. So if you think about a covalent bond, and let's say I have 2 chlorines, they each have 7 valence electrons, right? And when they come together, what happens is that those 2 electrons between them get counted by both atoms. And in the process of doing, they both end up with a full octet. So what we end up with is this shared pair in the center. Both atoms count the shared electrons. Okay? So we can have this lone pair where there's no bonding going on, and we can have a shared pair, which is the area of overlap. You can see that also in this ammonia, this NH3. The lone pair is a pair around the central atom that's not being shared, whereas the other pairs are considered bonding pairs. Okay? Just a terminology thing. So if we think about what's going on with fluorine, it's just like chlorine, 7 valence electrons for both. They both count the 1 electron between them that becomes part of this bonded pair, and they end up with a full octet. If we think about what's happening with oxygen, though, oxygen has 6 valence electrons. You bring 2 oxygens together, and if they count the overlap, then they only have 7 each. They don't have that full octet. So what they have to do is take one of the electrons from the area where there's a lone electron and bring that into the bond. So what I end up with is 4 electrons being shared, and we call that a double bond. Okay? Whereas the fluorine-fluorine bond is going to be a single bond. When I have nitrogen, each nitrogen has 5 valence electrons, and you can tell if I look at the overlap that it's not going to be enough, but even if I put 4 electrons in the center, then each only will have 2, 4, 6, 7. So I need to take the other lone electrons and move them in, and I end up with a triple bond where 6 electrons are being shared. So a terminology to know is bond order, and all that means is the number of bonds. So if it's a single bond, it's a bond order of 1, double bond is a bond order of 2, triple bond is a bond order of 3. If I have a single bond, I've got 2 electrons being shared. Double bond, I've got 4 electrons being shared. and a triple bond I have 6. So bond length is the next row. What do you think is going to be stronger, a single bond or a triple bond? Well, as it turns out, the more electrons that are being shared, the tighter those two atoms are being pulled in together. So they form the shortest length when I have a triple bond. Now for strength, this is the number of energy units. I believe it's probably kilojoules. This is the number, yeah, it is kilojoules. It's the number of kilojoules of strength it requires to break that bond. So the strongest bond is the shortest bond, and that's associated with the triple bond. The longest bond and the weakest bond is the single bond. So bond energy is another new term we need to know, and it's the energy required to break a bond. Now it always takes energy to break a bond, right? We learned that. So the bond energy in this case is the delta H, or the heat associated with breaking the bond, the energy that has to be put in. So again, if we think about what's happening with two hydrogens when they come together, the electrons from one are being attracted to the electrons of the nucleus of the other, causing some attraction. And as they get closer and closer, that attraction causes this potential energy to reduce. Now, if they get too close together and their nuclei start to overlap, they're going to have repulsion. And that repulsion is going to lead to this big increase in energy, which is undesirable, right? We want to go to lower energy to be thermodynamically favored. Okay. So the bond ends up forming at a length that is just the right distance so that we have more attraction and less repulsion in that bond. And that's the bond length. And it's also the bond energy. So we have distance here, which is the length of the bond, right, where the bond forms, and then we have the energy. So the energy associated with making that bond is the difference here between where it started as a neutral atom and where it ends up as a bonded atom. So that's where the bond's going to form. So the graph tells us both about energy and length. So let's do a practice problem. Here we have SF, SBr, and an SCl. So we're going to compare them for length. In all cases, sulfur is the atom, is one of the atoms, and we have 3 different other nonmetals. So if we just think about their size, you know, they're lined up in group 17 on the periodic table. Fluorine's the smallest, bromine is the largest. So if you think about what's going to happen with sulfur being the same for all of them, the attraction is going to be lower between the sulfur and the bromine because it's further away from that positive nucleus. So what you're going to end up with is the shortest bond is going to be the strongest bond, where the sulfur's electrons can get closest to the fluorine nucleus. And the longest bond is going to be the bond where there was more shielding, there was more distance between the electrons and the nucleus. So short bonds are also the strongest. Long bonds are going to be the weakest. Alright, in the case of, here we have carbon and oxygen in a double, single, and triple bond. And as it turns out, the more electrons you have in a bond, the more attraction you have between those electrons and the other atom's nucleus, and therefore the shorter and stronger the bond. So it looks kind of like this. The longest bond is going to be the single bond, followed by the double bond, and the shortest is going to be the triple bond, which will be the strongest. Okay, so the shortest and the strongest is the triple, the weakest and the longest is going to be the single. Alright, and we're going to stop there.